Hello students and welcome to today's lecture, which is going to be on periodicity, okay? Or, to realistically think about it, this is how you use the periodic table to kind of cheat on a whole bunch of properties of the elements on the table, okay? And this is going to be something that should seem relatively reviewish for some of us because of just the nature of chemistry. We end up using some of this periodicity type of stuff to explain a whole bunch of things. So first things first is that we're going to go ahead and take a look at our periodic table. And as we should remember from electronic configuration, that we have our S block here. These are where we have our spherical orbitals. We have the P block, okay? And the P block has 3 dumbbell-shaped orbitals. Then we have the D block, which is in the middle, and then we have the F block. And both the D and the F both have uniquely shaped orbitals. And across the top, we have our groups, and the groups are labeled 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way till 18. And then we have our periods, which end up going downwards, okay? So the first period is kind of like the first energy level of the atomic structure. And then the second period is like the second energy level of the atomic structure. One question that you could theoretically get from something like this is that it could ask you, okay, what element is at period 3, group 14 on the periodic table, and you would have to go down to period 3, group 14, and you would find that you have Si, which is silicon. And that's a typical type of question to see if you're able to read the periodic table just in its existence. There are other types of questions that you could have that are asking, like, what type of block is the element that's in period 5, group 8. And you would have to go down to group 5, 8, and see, oh, okay, this is ruthenium, and this is going to be a D block element. And that's the first kind of information or question that you could get from the periodicity section. Now we're going to go ahead and talk about some of the properties, and all of these properties can end up being related. They're all kind of similar. And the first property is going to be atomic radius. An atomic radius is going to be the diameter between 2 atoms of the same element from their nucleus here, okay? So the atomic radius, whenever we define atomic radius, we're going to define it as the difference between these 2 elements when they are bonded, okay? And atomic radius is going to be something that follows a trend where it relies on us to go ahead and look at the elements on the periodic table. So what happens here is that as we go from left to right, our size is going to decrease along the periodic table. And then as we enter a new energy level, that size is going to increase. So what we typically see is that as we go from left to right, we're going to get a small decrease each time. And then when we jump into the next energy level, we're going to get a big jump in size, and then we're going to slowly decrease in size. And what that has to do with is the fact that the energy level ends up getting filled up, so the electron then has to inhabit a new energy level that's outside of the previous one. And so every time that we have a new energy level, we have to put our electron even further out from that. And as we increase the number of protons, what happens is that those protons are then going to be able to grab hold of that outer energy level a little bit more strongly, which is why we end up having the small decrease as we go from left to right. Okay. And this is going to go ahead and show, this right here is the atomic number. Okay. And then what you'll see is that we also have our atomic radius, which is going to be size. And it does follow this exact kind of pattern where we have our initial jump, and then it gets smaller, 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 smaller. And then we get another jump, and then it gets smaller, smaller, smaller. Then another jump, and then it gets smaller, smaller, smaller. Another jump, then we get smaller. And then it looks like as we get to row 6, we get some oddball things going on. But that is our general path and plot, that we get a jump once we get into a new energy level, and then we gradually get smaller. Okay, and this is another way of kind of showing it right here. What you'll notice is that hydrogen and helium are kind of, oddballs here, but lithium is bigger and then it gets slowly smaller. Sodium is bigger and then it gets slowly smaller. Potassium's bigger and then it gets slowly smaller. Okay, and this is just our general way of explaining this particular thing. Next is going to be ionic radius. And ionic radius is going to be a factor that is reliant upon the fact that different compounds are going to lose electrons. And ionic radius is going to be a case where the ions are going to end up having a jump once we go from metals to nonmetals. Okay, so in our periodic table here, what we should notice is that sodium here is going to lose its electron. Okay, sodium has one valence electron, and when it loses that valence electron, its ion is going to be able to shrink down because it doesn't have that energy level. The same goes for magnesium. Its size will end up shrinking down because it loses those electrons. Whereas when we look at the P block here, these are things that gain electrons. So since they gain electrons, its size is going to increase from its normal size a little bit. Okay? And because it has that increase of electrons, and this one in particular takes 3 electrons, this one's going to increase the most. And then this one will take 2, this one will take 1. So those will increase less from their regular atom form. Okay? So across period 3, we should see that the ion size is going to be, this is going to be the largest for the metals, okay? Because it has 11 protons. And then at the ion, it'll have 10 electrons, okay? This one will have 12 protons and 10 electrons. This one will have 13 protons and 10 electrons. So as you can see, because of that pulling on those electron shells by the protons, we're going to get a little bit smaller. So it's going to be, this is going to be the largest, then it gets smaller, 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 way bigger, smaller, smaller. Okay? And so this will go ahead and follow this particular trend where we're going to go ahead and go slowly down. And then these are going to be where we have our 18 electrons, and then they go slowly down as well. Okay, next what we're going to do is we're going to go ahead and talk about boiling and melting point, which are important factors here. And boiling and melting point for the elements is going to be definitely determined based on where they are in the periodic table and what type of bonding that they'll be able to do. Often the easiest way for us to go ahead and tell this is whether they're going to be a metal or a non-metal. And just as a reminder, we used to have that there is a line right here that separates metals and non-metals, where metals on this left here are going to be a lot more likely to have a high boiling point and melting point, and that's going to end up being because of metallic bonding. Whereas the non-metals here are going to have a really low melting point, and that's going to be because of covalent bonding. They don't have the ability to do metallic bonding, okay? And what we have here is we actually have a way for us to go ahead and look at these things, both in terms of how the metal is bonded and how the oxides can end up being bonded. And what you'll see here is for the elements in group 3, the sodium, magnesium, aluminum, they all form a metallic lattice. And that metallic lattice is going to be something that's going to be really hard to melt. It's going to have a really high melting point. whereas silicon ends up forming a covalent network. And a covalent network is going to be where you have constant covalent bonding all over, kind of like in a crystalline-like structure. And if you think about quartz, that's what silicon really is. It's an example of quartz and things, and those also have a really high melting point. Whereas our covalent molecules right here, these are going to have relatively low melting points. And the same is going to be for when we have oxides. So when oxygen is bonded with these are going to form ionic bonds. And aluminum ends up making a special kind of ionic covalent layer lattice, but that's very specific to aluminum. And these are going to be also super high melting points, okay? Because we know that ionic compounds have a super high melting point. Silicon oxides, which is SiO2, which forms sand, also is going to have a really high melting point because it's still that covalent network. Whereas this phosphorus oxide and sulfur dioxide, are still all covalent molecules, so therefore they're also going to have a low melting point. For structures of chlorides, chlorides are still going to form an ionic lattice, okay? And ionic lattices are going to end up being things that have a high melting point, and then from aluminum all the way down to argon, those are going to be covalent molecules, and therefore covalent molecules are going to have a really low melting point. Okay. Next is going to be conductivity. Okay. Conductivity is basically going to be really high across the metals, and as you go across the row, what you should notice is that you should see an increase in conductivity across the metals, because in general they have more electrons that they can go ahead and add to that metallic bonding where they have that sea of electrons. And then you'll see that we get a big drop off once we finally get to our metalloids. And our metalloids are going to be where they have some slight conductivity, and then our nonmetals will have no conductivity. Okay. So conductivity will gradually increase until you get to the metalloids, and then it'll drop off drastically before it stops where we have our nonmetals here. Okay. The next is going to be ionization energy. And ionization energy is going to be highly tied to where the electron sits in the atom. So what I want you guys to notice here is that the things that have the lowest ionization energy also end up being the first things in their energy level. So for instance, when we take a look here, lithium, sodium, potassium, all of these here end up having a really low ionization energy. And ionization energy, again, is going to be that energy that comes from, or how much energy it takes to remove an electron from the outer shell. And what you'll notice is that these ones are the lowest, okay? This one ends up being the third lowest. And then once you get into the P block, the first one in the P block is actually lower than this one. And that should make a little bit of sense because we are adding to a brand new subshell that's kind of just right outside the S subshell. Okay, so anytime we enter a new energy kind of level, we end up getting an electron that's a little bit easier to strip off there. Okay. And this is going to go ahead and follow this same kind of pattern here. Okay, what you'll notice is that it'll go through the S block. It dips down just a little bit in the P block. It'll dip down a little bit as it doubles up in the P block. And then it'll go in this same kind of pattern as we go forward here. Okay, notice that this dip here is because we've added to the P block again. Okay, And this is a reminder, ionization is the energy it takes to go ahead and remove the first electron from an ion. Okay. And the other thing that you should notice is that the noble gases are the hardest to remove an electron from because they have the most amount of protons for each energy level. Okay, this is going to go ahead and close us out for periodic trends and this review on periodic trends. And, stay lazy.